Hello everyone. My name is Lian Longlin. I am a PhD student from Tianjin University. I am here to present my research on in situ deformation measurement of 3D printed scaffold and mechano regulation in tissue engineering. Osteoarthritis causes pain, stiffness, and loss of function in the affected joints, and can severely impair the quality of life of the patients. Bone tissue engineering is one of the most promising approaches for treating osteoarthritis. Bone tissue engineering aims to regenerate or replace damaged bone tissue by using non-materials, cells, and growth factors. The scaffold that mimics the structure and function of the native bone tissue and provides mechanical support and biological cues for cell attachment, proliferation, and differentiation. Mechanical stimulation can improve the effectiveness and success of bone tissue engineering. The International Research Awards on Design are presented to recognize outstanding achievements in the field of tissue engineering. Tissue-engineered scaffolds provide a temporary framework structure for tissue regeneration and provide a cell-engineered microenvironment for cell proliferation and growth through various structural deformation. Modulation of the mechanical microenvironment and that tissue regeneration and quantitative characterization of the mechanical microenvironment must be achieved. Quantitative elasticity engine of cells, tissues, and organs has become possible in recent years, thanks to the advances in modern technologies. Elasticity engine spans multiple scales, including the macroscale, the mesoscale, and the microscale. Among them, the mesoscale elasticity engine technique, optical coherence elastography OCE, has a spatial resolution of about 10 microns and a depth range of 2 mm, making it suitable for tissue engineering applications. Three-dimensional printing is a powerful technology that can create complex and customized structures with high precision and resolution. Three-dimensional printing has been widely used in tissue engineering. It is important to measure and understand the deformation behavior of three-dimensional printed hydrogel scaffolds under different conditions. The macro-CT and digital volume correlation (DVC) has been developed and applied to measure the three-dimensional strain and deformation fields of the scaffolds. Due to the low spectral absorption of water in the wavelength range in which the October technique operates in situ, in vivo measurements as well as three-dimensional reticulated material studies based on bound materials can be realized.
At present, the available methods to anticipate the differentiation properties of stem cells rely solely on computational simulations. Recent developments in representing the cellular microenvironment schematically within tissue engineering scaffolds have demonstrated that scaffold structure can be engineered to facilitate tissue growth in predetermined regions and approximate the laminar mechanical properties of natural cartilage. The microstructure and pore architecture of scaffolds significantly affect the fluid accessibility of various locations. Thus, it is imperative to formulate experimental techniques for anticipating stem cell differentiation outcomes.
The printing matrix and the fabrication schematic diagram of scaffold. The mixture of thick fibrin and type 2 collagen with a mass ratio of 7:3 was used to prepare the scaffold for bone and cartilage tissue engineering through a three-dimensional bioprinter. The CAD models were created by UG Unigraphics NX, Siemens, Inc., Germany, and imported to the three-dimensional bioprinter for printing. The extruded printing matrix is rapidly solidified and shipped on a low-temperature platform. The printed scaffolds were dried in a vacuum at 68.5 degrees below zero for 36 hours. Then the scaffolds were immersed in absolute ethanol, sodium hydroxide solution, and ionized water sequentially. To characterize the mechanical microenvironment of tissue engineering scaffolds, a COCE method proposed. This method includes two parts. One is the literal component identification of the scaffold, and the other is the developed SCDVC method to measure the deformation field of the effective components. To evaluate the COCE method, the effectiveness of the component identification algorithm was investigated. The proposed algorithm can better obtain the three-dimensional image contour boundary features of the geometric shape of the three-dimensional printed scaffold, resulting in better connectivity of the three-dimensional image contour. The segmentation process does not require human intervention and is highly automated. The histograms show that component identification can also be better achieved for tissue engineering scaffolds with different water contents. With the help of the component identification algorithm, the SCDVC algorithm can obtain the deformation field of the real structure of the tissue engineering scaffold. In contrast, the conventional DVC algorithm cannot distinguish the non-material involved parts, and shows the deformation results of the whole scaffold construction space. To evaluate the COCE method, the effectiveness of the accuracy of SCDVC algorithm was investigated. The October volume images of the tissue engineering scaffold with the predetermined stretch deformation in three directions are applied by the inverse mapping method. With the help of the component identification algorithm and the improved SCDVC method, the pores of the scaffold avoided during the deformation measurement ensure reliability of DVC. The COCE method can obtain the deformation field of the scaffold architecture with subvoxel accuracy. The discrepancies between the displacements obtained by MSD in the three directions are less than 0.0023 voxels, indicating that the accuracy of the method is isotropic in the three directions. The OC measurement system includes the swept laser source October SS October imaging system and the excitation device. This study used a miniature in situ mechanical test system to apply predetermined loading to the tissue engineering scaffolds in vitro. Two October scans were emitted before and after the deformation of the tissue engineering scaffold. The multiple A scans of the specimen were reconstructed into B-scan cross-sectional images. The volume images of tissue engineering scaffolds were reconstructed from multiple B scans. In the tensile experiment, tensile displacements from 0 to the 500 micron in increments of the 100 micron for 6 loading stages were set. The loading rate was 20 micron per second. After loading, the test system was paused and the image acquisition was completed by entering the acquisition parameters. The influence of October image noise and deformation. The correlation produced larger measurement errors when characterizing the actual deformation of tissue engineering scaffolds. The displacement fields and strain fields of the scaffold under unique field tension. The displacements change linearly with the length in the tensile direction, which portrays the detailed deformation of the real structure. The inhomogeneous strain fields are possibly caused by the structural features. The loading applied to the scaffold is redistributed by the sandy scaffold architecture from the mechanical microenvironment inside the scaffolds. can investigate the effect of water contents on the mechanical microenvironment of the tissue engineering scaffold. The strain fields of the tissue engineering scaffolds with a water content of 824%, 363%, and 81% were measured under stepwise unique tensile tests to investigate the effect of water content on the mechanical microenvironment. The scaffolds with different water contents show different structural characteristics. The strain fields of tissue engineering scaffolds become larger as the water content decreases. When deformation occurs, the lack of water causes the solid part inside the tissue engineering scaffolds to be subjected to greater loading, resulting in a greater loading in each internal region and an increase in the overall strain fields. The water content significantly affects the mechanical microenvironment of the scaffold. The identification algorithm proposed to identify the composition of the scaffolds is not sensitive to the culture fluid, which will facilitate in vivo measurements. To achieve the prediction of cell differentiation phenotypes by experimental measurement methods, the SOC method and mechano-regulation theories were combined. The mechano-regulation theories provide the relationship between tissue differentiation and mechanical stimulation, which has been incorporated into computational models of tissue regeneration as a predictive tool. This theory combined with the proposed SOC method allows the characterization of the mechanical microenvironment of the engineering scaffolds in a realistic environment. 3D strain fields are extracted from the OC images before and after deformation. The deformation excitation can originate from either artificial excitation or physiological excitation. The mechano-regulation theories are concerned with tissue shear strain, which can be obtained from the primary strain in three directions. MSCs can differentiate into fibroblasts, chondrocytes, and osteoblasts based on mechano-regulation theory and defined 3D tissue shear strain fields. The effect of different loading levels and water contents on MSC's differentiation was studied based on measurements of tissue engineering scaffolds. As expected, the proposed SOC method can quantitatively measure the shear strain field on tissue engineering scaffolds required by the mechano-regulation theory, and further visualize cell differentiation based on the shear strain field. Both in vitro loading and water content significantly affected the tissue shear strain within the scaffold. At the same water content, the greater the in vitro light displacement, the greater the percentage of chondrocyte differentiation phenotype. The lower water content, the greater the percentage of chondrocyte differentiation phenotype at the same applied displacement in vitro. Based on the proposed method, it is possible to achieve the regulation the phenotypic percentage of stem cell differentiation phenotype.